And I think next we have Justin Williams. Hey, hello, Justin.
How's it going, Alberto?
I don't know if Warren, are you around?
Justin, have you shared your deck?
All right, doing that now.
Okay, so I'll let you guys go ahead, and as soon as you're done with the intro, I'll move to the deck share mode.
Yeah. So, well, Justin is a senior WebRTC developer. We are in the same team, WebRTC Ventures. He's joining today from Canada and going to talk about best practices and philosophies for WebRTC applications. I think it's a pretty relevant topic today when everyone is planning to build the next live streaming unicorn or this huge application. You want to start with some good fundamentals, and yeah, just how do we build for these applications for success? And yeah, please go ahead, Justin.
Yeah, exactly. Thanks, Alberto. That's a great introduction. So yeah, maintainable WebRTC applications. To be honest, quite a bold claim by me, Justin Williams, at WebRTC Ventures. But let's get into it. So just a little bit of background about me, just for context. So yeah, as Alberto said, senior developer at WebRTC Ventures. We work with various clients to offer consulting and contract work to build out full stack WebRTC applications. So throughout my career, I've seen applications grow from the kind of startup hacky code to code that runs in production, and I've seen kind of good sides of this and really bad sides of this. And for this presentation, I'll be going over some high-level sort of design philosophies and approaches for developing maintainable WebRTC applications. We'll consider maybe a generic web application and have a look at some best practices used for development to enable, I guess, the developer to maintain the application's architecture. So, I mean, these points really will work well in any web-based application, but I'll be pointing out sort of the key parts that are related specifically to real-time calling applications. So kind of mostly we'll focus around the architecture for integrating your application with a CPaaS, and then specifically around component-driven architecture development for our architecture. So as many of us know, today's world of web-based application development, we make use of a lot of services, hosting, various tools offered by cloud providers for our application development. And kind of what these tools do, which is really nice, is that they abstract away very complex details or workloads and configurations away from application developers, so that as an application developer, you can just focus on your application development. And what these end up doing is these tools accelerate development by letting you just focus on that application development side rather than having to worry about managing infrastructure. So a CPaaS, of course, offers communication service integration in a similar manner for our WebRTC applications. And I think, as many know, self-hosting media infrastructure can be a really huge task. And if you're unable to, staff teams to maintain and develop media structure efficiently, that can be a big burden on your application developers if that's what they have to worry about. Obviously, you wouldn't be hiring application developers to manage infrastructure, but that's kind of, what it looks like. But working with libraries offered by a CPaaS that integrate with an application, they don't only add benefit for the hosting side of things, but to the developers and the product owners having an idea of what the CPaaS offers. You're kind of looking at it from an abstract point of view, and having that kind of like enables you to talk nicely with your product owners about features and stuff like that. So that they're aware of the context of what you can do, and based on that, you can kind of communicate nicely to plan out how you want to build out different things. So, while the WebRTC spec has come a really long way to being able to be used directly in applications, it's still, like, as we know, really large and complicated to integrate and maintain easily, for long-running applications. Obviously, since signaling is not part of the WebRTC spec, it's kind of another problem that you'd have to worry about. So the signaling, I guess, is tend to be tightly coupled with the hardware and the software for the media servers. So having both of these aspects managed by a CPaaS saves a large amount of time and effort. As I said, the libraries abstract away the WebRTC implementation details, by the CPaaS providing high-level client APIs that implement this WebRTC functionality for us. And thinking about those APIs from the abstract point of view kind of lets you simplify your architecture's design. And the application development can be just focused around only the feature development and the business logic from your application. And then apart from abstraction, many CPaaSs tend to offer a lot of tools and services, allowing developers and product owners even to do things like control connections, get usage insights, and help customers diagnose issues and that sort of stuff. So that's kind of nice to have for the CPaaS. Sorry. But yeah, so with that, you kind of get rapid development done, and that helps you get to market really quick, or quicker than normal if you had to implement and maintain all that stuff yourself. But a large user base might have high expectations on quality. And I think many people might know that quality is really tough to deliver if you're working with the unmaintainable code base. A lot of the times you can see the effects of unmaintainable code being added to your code kind of right away, right? Somebody works on a feature, they get it out the door, and then all of a sudden requirements change, and then you want to make maybe a small change to a big change to your application. And if you're doing that with a brand new app, that might seem like a really quick and easy change to make. But once you have a whole bunch of business logic in place and you're trying to add these new features, then all of a sudden it's like, why is this so hard to integrate and change? The code is really messy, it's spaghetti code kind of thing. And that mentality, kind of breaks down the team a little bit, and it just makes development really hard overall. And then, from there, what tends to happen is teams start to grow. So, your managers might hire more developers, and then you're trying to get features out the door quicker, and you're finding a lot of problems. So then maybe you hire more QA, and this increases development cycles more and more, and features end up taking really long to get into production. This figure I would think is quite popular nowadays. It's from Jason Gorman's presentation at SBA Software Practice Advancement Conference back in 2011. So it's just for illustration. This is not the original data. I encourage you to check out that link if you want to get the context behind it. But basically from the figure, we can see that as more releases are done, we get a spike in cost per line of code. So this is a simple metric, and it might not be the same for every project, but it points to the common problem for many application projects that which is that they become very expensive to maintain over time. Inherently, you're going to, I guess that's kind of, depending on how you look at this, maybe you do want to have more expensive, you want to be able to write less code to give you more features. But another way to look at this too is if you end up having to write a lot of code, but by a lot of developers, that's really, really expensive. Not to mention, nobody really wants to work in a messy code base, so it kind of ends up being a really, really bad thing. So the main problem that we're trying to solve then is how do we manage our changing requirements? So it's the major cause of unmaintainable code, and it's pretty much present in every project. This is how we see where component-driven architecture can offer a huge benefit if you follow that approach. So with an application's architecture specified into clearly defined components, you can then relate them into feature functionality and their requirements, and then you use your design to change or meet these new requirements. And this can all be done while you're trying to keep the code maintainable. So component-driven architecture does kind of require that the code is written in a clean manner from the start, following things like the well-known solid principles of clean code. These types of principles will enable component-driven design. However, I'm not going to be covering them in this presentation because I'm not going to be able to do them justice, but I'll recommend reading Robert Martin's work along with checking out other online resources. Obviously, I think that's like de facto standard these days for software developers. And this talk was kind of inspired by his clean architecture approach as well. So, a big benefit to component-driven architecture is how it enables us to separate out dependencies from our application logic. So a dependency library you can integrate maybe with a wrapper class, and maybe surrounded by some modules and a component to form a dependency. And then this can be, doing something like removing removing magic strings from your code base. So say you have a bunch of URLs, or maybe you integrate with something like S3. You have a bunch of strings and paths everywhere because you want to keep everything consistent. But if you have that spread out of your code base, those magic strings and numbers and whatnot are going to be really messy to deal with. But if you can wrap them up into a component that's commonly used throughout your application, this results in a lot cleaner code. We want to be able to understand how changing the code in one component from there affects other components that use it. And having this type of modularization allows us to have a clear distinction between our components. And what this does then is it lets refactoring and building out new logic be a lot easier, way safer, and just more maintainable. Here we have a simple component diagram showing some of the separation concerns for some generic web application, right? So we see here that we have our application and it's dependent on some views and some presenters and a data store, pretty standard. We have our views that also depend on our presenters, and presenters depend on the store. And our store is using an HTTP plugin and a WebSocket plugin to send and receive data. So this is a very high level. Obviously, we might expect there to be many classes for our views and presenters and so on. But within our views, maybe we could have some component separation in there to distinguish between maybe pure UI components, functional components, class components, or nested components, kind of depending on what framework you're using. But I'm kind of capturing that in just one top level component here. Likewise, maybe presenters too, that probably has a ton of business logic in them. So we can probably get some good component separation in there as well. But the higher you are with your component diagrams, the easier it is to see dependency relationships. It is a bit tough to see the amount of code that is dependent on the various components from this view. But from this diagram, you would assume that there may be a lot of presenters that are dependent on the store. So if you make some changes in the store, it will cause all your presenters to change, following by the views that need to change, right? But the important thing around components is that they contain classes, modules, etc., that have a clear purpose. So understanding the purpose of a common set of code will help us organize it clearly to maintain it easily. This simple component diagram does help us understand where we would need to write code. That is, what component should contain what logic. So from our design here, we see that the store has a dependency on the HTTP plugin. So we would expect to see any new requests that you add to your application into the HTTP plugin and maybe offer that as a new API to be used by the store or wherever. If we see some code going in where maybe a presenter of views are directly using the HTTP plugin, then our architecture is broken. But that's fine, because either we update the architecture to match what we want, or say we want to keep our architecture the same so we can refactor out the code into the store to not mess with our dependency chain. We also would expect not to see any magic URLs of strings being passed in as parameters to the HTTP plugin APIs from the store. So that would be an implementation detail from the HTTP plugin leaking into the store. So obviously, as good developers, we'd refactor that out to keep the separation between the store functionality and the HTTP plugin functionality. That way, if you need to refactor or change a URL for specific HTTP requests, we're only changing that in the plugin, and we're not changing that everywhere we want to make that same request in our store. So not everybody might agree with this exact design. Maybe some developers would prefer other design patterns. Maybe they would prefer to let the presenters have access to the WebSocket plugin and the HTTP plugin so the store doesn't have to do all that work. But that's fine, right? The idea of this component dependency graph allows us to visualize these details and decide how we want to make changes. Now with this knowledge in place, let's maybe take a look and see how we might integrate a new service into our architecture. So here we see one approach that we can take to integrate a CPaaS into our application while keeping our components and their architecture in mind. So we've kept the same architecture as the previous slide the same, but we've added in a bunch of new components to facilitate a CPaaS integration to add video calling functionality into our application. So at first, this might seem like a lot of components just for one dependency, but let's maybe get into why that would be a sensible approach. So at the top, we see our set of CPaaS components, so the CPaaS library. I've just put it into a component. But we can think of this as the CPaaS SDK or its client-side library. And then from there, we have a component that will implement the CPaaS library. So this component would wrap the APIs of the library, and it will contain maybe some common logic that you'll always need to provide to these APIs for your application to use. So the component implements, as you can see here, a call service interface, and this call service interface is defined somewhere in our application code. So this call service interface is designed to be, or to provide very abstract APIs to the rest of the application. So you're at that point of view, you're focusing on just facilitating the needs of your application, and you don't care too much about the implementation details for your CPaaS. If we ever need to change or upgrade our CPaaS library into a new major version, or if we want to switch to a new CPaaS, our call service interface largely, hopefully, will remain unchanged. And hopefully the rest of the application will remain unchanged as well. We just need to implement a new CPaaS integration. Depending on how our application was integrated before, maybe we're using a framework like React or Vue, the call service implementations can be indirectly integrated with our application code via maybe like a plugin. So the plugin would contain logic that's specific to the application framework. It knows when it needs to initialize, uninitialize, maybe set up event listeners and tear them down. And this plugin could integrate as well nicely with the store that we have, particularly if it uses a library like Redux or Vuex, and we'll see why that could be important a little bit later on. We also have a component to group together some UI components that we use for our calling functionality. So these might need to be a bit more tuned to the CPaaS library, depending how you integrate it. Maybe at first they will be. The CPaaS library might require, for example, that we create video HTML elements and then we pass them into the CPaaS APIs as a reference. But maybe then some other CPaaS libraries can create that video tag for us. So it's a little bit different there. But the main thing is that you want to maintain the relationship between your UI components, the plugin, and the CPaaS. We really want to clear a separation of concerns so that when requirements change, code changes are easy and reasonable to make. So we know where we want to add new code in order to keep our code base clean and the architecture intact. So while the application grows and you add features, there'll inevitably be refactoring between the various components. Maybe we might write a lot of logic in our call service plugin that over time we find can be refactored into the CPaaS integration component on the top there. Or maybe we see that we can move some logic from the integration component into the plugin and that sort of thing. So this is where we start to see a use for the distinguishability between stable and unstable components. So component diagrams can be drawn to show the relationship between the application code and the dependencies involved. So from here, you can draw a dependency graph, and this dependency graph will show what areas of the code base are stable and what areas of the code base are unstable. So stable components, briefly, they are generally not easy to change. They might have many components that are dependent on it. This means that if you want to make a change in the stable component, that would mean that all the dependent components would have to be changed or rebuilt, of course, depending on what language you're using and so on. Unstable components tend to be pretty easy to change, at least hopefully. They generally will have many dependencies with little to no components being dependent on it. Unstable components are easy to change, but they will have to be changed, or most likely have to be changed often if their dependencies are changed. So stable versus unstable components, not necessarily a good versus bad thing. They exist in any project, and they should be embraced. So for maintainable code, it's important to distinguish between your unstable and stable components and know where they are. Stable components should be really well defined, and they can provide its dependence with abstract APIs such that that implementation of the component is irrelevant to the dependent. So stable components generally would be really nice if they had little to no business logic in them, since the business logic is where you're changing quite often. Unstable components, you want to embrace them. You want to be like, okay, these are going to be changed often. And then maybe this is where you keep your business logic, because you know that they're easy to change and they're using all your dependencies. So they kind of know how everything works. And you just want to embrace the fact that these are going to be changed often and hopefully make that an easy process for you. So here we see a bit of a distinction between our stable and our unstable components for the same architecture. So we want our external services for our application to be formed into stable components. It's really important to have these components be clear and simple in their purpose. They end up being critical components to our architecture, of course, and they're used in many places in the more unstable code. So grouping these components as moderately stable here that I have in the middle, that's a little bit weird to at least label them as moderately stable, but achieving a really perfect architecture is quite difficult. So the goal would be to have these components be stable, but as features are built out, we see that some components may need to adjust their purpose, or maybe be separated into multiple components, or have code move up and down between them. So the requirements of the application might change, and the effect of that in terms of the code should just be to change the logic of where we want those changes, and not have to mess with like the external code or the external integration components. You just want to be focusing on changing where your business logic lies. An example scenario for this could be your initial implementation where the application, it just was a standard web page. It showed a video call and it showed all the users in the call. You have some publisher and subscriber classes created within maybe our call component there. So we can publish video and audio, and then you have subscriber components to subscribe to the remote users' audio and video. And then after some time, we want to update the application to maybe be as fancy as this application is. You want to be able to change layouts, let users pick and choose the layouts, drag and drop, all that sort of stuff. So this might mean we're all of a sudden going to have publisher classes in multiple places, as well as maybe some more subscriber classes, and their usage is now a little bit different. So there'll probably be some refactoring involved where the code from the call components and the views are probably going to change. But ideally, if the call components were created very cleanly, you're just changing the code in the views that have to add in the extra classes. You're just adding maybe some new components to your views, but hopefully you're using the call components as they are. Maybe a little bit of refactoring there to facilitate what you're doing, but hopefully not much. So there could be some code in the views that maybe lifted up into the component as you build out more features. Maybe initialization logic or configuration is changing, and then maybe some more separation within the call components as well. But once we have our CPaaS integration settled, we want to have to not touch that implementation and focus on where our components that use it, regardless of this actually being the case. Keeping the separation between stable and unstable components will allow us to make those changes a little bit easier. So once a CPaaS has been vetted and chosen for application, it's quite beneficial to abstract away the integration, kind of as we've seen a little bit, but we'll get deeper into that. So we've seen with our component architecture, it's good to have that abstraction layer to implement the CPaaS integration with. Lets you change the CPaaS a lot less effort, and we'll see that. This methodology also allows us to make changes to our application code without worrying about the CPaaS integration as well. So you'll have the wrapper APIs implementing an interface that you have defined somewhere in your application code, and that will maintain a clear and strict dependency graph between the application components and the CPaaS integration component. So this ensures that the application can be refactored easily without having to worry about breaking your implementation details for your CPaaS. And you can change maybe your CPaaS integration as well without having to worry about your application. Here's a UML diagram, kind of a deeper look about the CPaaS integration with this UML diagram. So the top, we have our CPaaS SDK or library, and it offers a few classes, maybe a top-level faucet class, maybe a class to represent a single stream, like a publisher or a subscriber. The CPaaS library is integrated with a call service implementation component, and this wraps the CPaaS library's APIs. So the call service implementation implements the call service interface that we define in our application. So this could account for hopefully the minimal business logic necessary to work with these CPaaS APIs. At a layer of abstraction, we want to achieve, we have a layer of abstraction that we're implementing against that will be used by our application. So we'll have our application potentially also define multiple interfaces for every concern that it cares about. So as we go deeper, we can see our call service plugin uses this call service interface. We see that we have a call service factory back up on top in our CPaaS integration component that's used to construct our call service. And this will then be used by the call service plugin to control the life cycle of the call service implementation. So the call service plugin, it knows how our application and the frameworks work, and it's the integration point for our application's framework. So depending on what framework you use, there'll probably be different areas where you need to initialize and set up event listeners and so on. This plugin will know how to do that, and it'll do it at the right times. The plugin can also know how to format the data being sent to the application from the CPaaS and back and forth. We have some libraries like Vuex, which can do crazy things to JavaScript objects as soon as you pass it to Vuex view or part of the store as well. And those are adding observability to those objects. And we know the objects in JavaScript are passed by reference. And this can cause really weird issues if we provide objects from the CPaaS library straight into our store. If the CPaaS library was to update these objects outside of the application framework expecting it, you'd probably see some issues there. But this is the benefit of the plugin here. It knows the application details well and will account for these sort of nuances. It provides a clear separation of concerns between your CPaaS code and the application code. You might have the store being used to integrate with the plugin, indirectly accessing the CPaaS APIs. The plugin can be designed to populate the store as well somehow with information from the call service, as I said. So maybe a possible use case here would be the CPaaS API for creating a publisher. It might allow us to specify metadata for the publisher. So that could be user IDs or configs to define user behavior, like a role or something like that. And then on the remote side, when the CPaaS library sees that a publisher can be subscribed to, it can then access that metadata. Now, maybe the CPaaS you're working with has a limitation where you can't change this metadata once it's been set. But our application is growing and changing, and we now want to be able to allow users to maybe change their display name or change their role or whatever that's part of this metadata. And at that point, you might have to do something like integrate back into our WebSocket or our HTTP plugin our custom application logic. And that's what you'd use the store for. The store will then provide all this data from the CPaaS and your new data that you're changing. And the store can have the logic to organize the data between these and give them to the presenters or to the views. So we kind of see here how component architecture helps us make decisions to keep our code clean by separating our concerns nicely. And then we see now how we can make large changes to our code quite easily. So here we see that this is what a pretty large code change would probably look like. But without too much effort in this design, we can cleanly implement a new call service implementation to integrate a whole new CPaaS. So our call service APIs, if they're defined clearly enough, we can add a CPaaS without touching much of the application code. We only need to add in new classes to implement the CPaaS to adhere to the call service interface. We probably will have to do some plumbing and refactoring to change APIs and configs, but this would be minimal, hopefully, and easy to spot. Then we just update our factory to create a call service implementation of your choice and pass that along to the rest of the application. So this easy and clear separation not only allows us to easily migrate to a new vendor, but it could allow us to do things like A/B test the CPaaSs, revert between them easily. And this could be like a huge benefit if now you have the staffing where you can host your own infrastructure. And then with the effort of achieving a clean architecture from the start, we can start to make these sort of major changes that would normally take months to years down to just way less time. And then the last thing to touch on with the clean architecture and component-driven approach is to avoid over-engineering. So it's quite a tough line to draw and might seem a little bit ironic based on the presentation, but the main idea is that you want to keep the architecture flexible. It should be easy and even quite willing to change. You want to avoid locking into a specific pattern or library, and you want to have the expectation that everything is probably going to change. Avoid writing more code than you need to. Write clear code for your current requirements with just the idea and visualization of how you can change the architecture to meet new requirements. But avoid doing things like writing crazy base classes with a bunch of logic with the idea that these can be extended via layers of abstraction to facilitate these new requirements that you don't even know about. It's tough to predict how requirements will change and tough to predict how it will affect the architecture if those requirements are unknown. So just don't solve for unknowns. Stick with your recommended approach for your application integration so that the code base kind of makes sense if you're Oh, we're at the
Yeah,
end.
sorry, Justin, that we are almost there.
Okay, last point. Keep it simple,
Yeah, just
and that's where I wanted to end.
okay. Sorry to cut you there. I wasn't sure if you had more, so I just wanted to make sure that.
No, that's it. That's it. I was blabbering on a lot. I got really invested.
No, thank you so much, Justin. I think there are a few lessons there for probably everyone to keep in mind. I know
Exactly.
this is the end of this track, so probably we can have like, even it's already the end, I don't know, Warren, if you could have like one or two questions if someone has, or we should.
Sure, go ahead and ask a quick question. We've got a 15-minute break after this, and then at 2:30 we've got the IoT keynote with Henning on the main stage. So take a minute if there's a question or two, and then we'll take a break.
Cool. Yeah, if someone has some questions, as I said before, raise hand or write on the chat. Yeah, I have a couple. Well, one was about if you keep track of the component architecture design anywhere for the documentation, and what tools are good to use for this.
Yeah, for sure. I mean, I think the high-level component architecture is really important to keep documented. This allows you to visualize changes with your team a lot easier. And if you hire new people, they can come in and sort of know what the code base looks like right off the bat. And for tools, I just use Plant UML with IntelliJ or VS Code, and I commit that straight into the code base.
Okay. Yeah, the other one was about if you recommend having all the UML diagrams as part of the documentation.
Yeah, and that, as we saw the UML diagram that I showed in the slide, that one started to look a little bit crazy, and that's probably missing tons of classes and interfaces and so on. UML is quite a tough one, especially if you're doing it by hand. I wouldn't recommend including too much of it, but it's a great tool to use if you want to, discuss and deliberate implementation details with your team. The problem is that your code changes way more often than you would want to update the UML diagram. So try to keep that usage minimal.
Cool. Yeah, I don't know if someone has any questions there, or no. No. Yeah, we have the other talk in around 12 minutes. Yeah, but what you were mentioning in the last slide, how do you know when you are over engineering?
Yeah, I mean, yeah, that can be quite tough, but as soon as you're starting to write code for requirements that you don't have yet, maybe you're thinking that your code can work in a certain way. Maybe you want to write some crazy base classes, like I said, that do some functionality, and you're expecting it to be extended by many layers of abstraction. That can be way more painful for other developers using it. And if you're realizing that making these code changes here is a lot of effort, then you're probably over engineering at that point.
Got it. Yeah. Definitely. If it looks like too complicated.
Yeah.
It
Sometimes
is.
you might see some base classes that are just abstract and only define abstract classes, and there's levels of that. That's probably a red flag.
Great. So yeah, and then wrap up here. Thank you for joining, Justin, and everyone for listening. And yeah, see you around. Bye.